Hello friends, this video that I'm going to make now is directed towards students, secondary school students who may be in 9th or 10th standard of international schools studying IGCSE or for IB Diploma. And in this video, I'm going to do something that is exceedingly simple. I'm going to talk about relative velocity in one dimension. So the concept of relativity that we'll talk about now was, as far as it is known, was first propagated by Galileo, and therefore it is known as Galilean Relativity. And Galileo gave an example. It goes like this. Although Galileo talked about a ship, I don't think many people travel in ships anymore. So I'm going to talk about the compartment of a train. So you can imagine yourself being inside the compartment of a train, and that train has no windows, it has no doors even, and suppose when that train travels, it's exceedingly smooth. So you can't hear any noise, there are no vibrations coming from anywhere. So Galileo says that if you are in such a compartment of such a very advanced train, and if the train is traveling at a constant velocity, that is, its speed is constant and the train is not changing its direction, you won't be able to tell whether the train is stationary or whether it is moving. So if you are inside the compartment of a train, and the train is such that when it travels it makes no noise, there are no vibrations, and there are no windows and no doors, so that you can look outside and compare your motion to objects outside the train. In such a case, if the train travels at constant velocity, that is, its speed and direction remain constant throughout, you won't be able to tell whether the train is moving or whether it's not moving. And from here you can deduce that there is no such thing as absolute rest or absolute motion. All motion is only relative motion. So if you are inside such a train, with respect to yourself, you will always be at rest. So even if a person is moving, he only feels that he is moving because of the strain that he exerts on his muscles, and because he can compare his motion to objects outside, maybe stones and trees or anything else. So, but in the ideal sense of the word, even though you may be moving, with respect to yourself, you are always at rest. It is only with respect to someone else that you are either at rest or you are moving. So whenever you are moving with respect to yourself, you are at rest. Even when you are at rest, you are obviously at rest with respect to yourself. When you are moving maybe with respect to someone else, but you are at rest with respect to yourself. So whenever we talk about motion, it's important to state what the motion is in respect to. So when you are traveling with respect to somebody sitting inside a car, maybe if the car is traveling at the same speed as you are, with respect to the person inside the car, you will be at rest. And maybe if the car travels at a much faster speed than you are running, then with respect to the person inside the car, you will be traveling opposite to the direction of the car. So whenever we talk about rest and motion, it's necessary to specify with respect to whom. The observer is important. There's another example which I read in one of Brian Greene's books. It goes like this. Suppose two astronauts, maybe you and your friend, they are sent to somewhere in outer space, and the two of you are in such a part of outer space that you can't see any stars, you can't see any asteroids, you can't see any objects altogether. It's absolutely dark. So it's completely dark. You are in the both of you are shrouded in complete darkness. Now, the space suit that you are wearing has a red light on it, and it keeps blinking. It goes on and off at regular intervals of time. And the space suit that your friend is wearing has a blue light, and it also blinks. It goes on and off at a particular frequency. So this is you, perhaps, and this is the red light that is blinking on your spacesuit, and here's your friend, and here's the blue light that is blinking on his spacesuit. Suddenly, you see, of course you can't see your friend, all you can see is the blue light that is blinking, that's going on and off. All you see suddenly is that the blue light approaches you. It comes towards you and gets closer to you and closer to you and closer to you until it passes you and goes in the opposite direction. So you see a blue light which is blinking and it's coming towards you, and it, after a certain point of time, it crosses you and goes to the other side. All the while you will say that I was at rest and the blue light came towards me and it crossed me and went to the other side. But what will your friend say? Your friend will say that I am at rest and it's the red light that came towards me, blinking and blinking and blinking until it crossed me and went in the other direction. So this is a very good example of saying that there is no absolute rest or absolute motion. Motion and rest are always with respect to some person. The observer is of course important. So how do we incorporate that into physics? We incorporate this, I won't go into the details, we incorporate this by saying, say this is some person A, this is some other person B, and the distance between them is d. The person A is traveling towards B with a velocity v1, and the person B is traveling towards A with a velocity v2. So the relative distance between A and B will get covered in lesser time than when if either of these two were stationary and only one was moving. So it's because both of them are moving, the distance between the two will get covered more quickly. And we say that the time that will take for A and B to meet at some point, maybe here or here or here, depending on whose velocity is more. If A's velocity is more, maybe they will meet here. If B's velocity is more, that is, if V2 is more than V1, perhaps they will meet here. If both have the same velocity, they will meet at exactly the midpoint. The time that is taken is d divided by V1 plus V2, and V1 plus V2 is called the relative velocity. In a very similar way, if A and B were moving in the same direction, the relative velocity would have to be subtracted. It would either be V1 minus V2 or V2 minus V1, depending on whose velocity is more. So this is the very fundamental basic concept of relative velocity. Another way in which you can think is, I said that the distance between A and B is d, and they are both moving towards each other, one with velocity v1 and the other with velocity v2. But this is from the perspective of a third person. What will A see? A will always say that I am at rest. And to incorporate that, you can imagine giving A an opposite velocity v1 so that A comes to rest. And because you have added an extra velocity on A, you will have to add the same extra velocity on B, and therefore now we are ready to state the entire problem from A's point of view, A will now say that I am at rest, because these two velocities, they are equal and opposite and they cancel each other out, and V1 and V2, because they are in the same direction, the total speed of B will be V1 plus V2. So from A's point of view, A will say that I am at rest, and B has a total velocity of V1 plus V2, and it is B who covers the entire distance D with the speed V1 plus V2. Similarly, from B's point of view, B will say that I am at rest, and A covers the entire distance D with a total speed of, net speed of V1 plus V2. That net speed V1 plus V2 is the relative velocity between these two objects. So as this is a sample video, I won't elaborate anymore. So we'll end here. Thank you.